Okay. Oh, a little loud. Sorry about that. Okay. All right. So we continue onward. Again, these are all old facts, so I won't repeat them today because hopefully by now you've memorized them. But these are things which I hope you remember even after you've taken this class for at least one more quarter, hopefully two. So what did we talk about last time? So last time we finished talking about local linearization, and this was from the section which said tangent lines are great. And in particular, if I want to find the line that best approximates the function f of x at x equals a, or I really should say around x equals a. And the idea being if you look close enough to that point, the function looks like a line. Well, it's a tangent line. So when we talk about finding a local linearization, we're trying to say, well, f of x looks like what line? Hence, you see the word line inside this word. And so simply put, the linearization is the tangent line. So I might ask, what's the linearization at a point x equals a for a given function? And really it's just asking, make the tangent line. Then we jumped into the next section where we focus on max and mins. Now max and mins, intuitively we know what max and min means. Max says you're bigger than everything else. Min means you're smaller than everything else. And there's two kinds of max and mins. There's a global, and a global says I have a function and I'm looking over some range for the x value, some interval. So the global max is where it's bigger than all the other x values I could plug in. And in particular, I'm looking for an actual point which I can plug into my function. So I'm not looking for saying my function is bounded above by this number or it's bounded below by this number. I'm saying there's some actual point I can plug in, and that is the largest the function can ever get. Similarly, the global min is it's a point where I plug into my function f of a, and it's less than or equal to f of x for all x that I might be considering for my interval. Another idea, instead of thinking about global min, global max, is local max and local min. So still max, min, so we still have the same idea. Max means you're bigger than what other values. Min means you're smaller than other values. But instead of looking at all possible x, the idea of local is you look for x near our point A. So for instance, I would say a local max is one where if I look just close to A, close enough, narrow my vision, then I say, aha, it's larger than everything else nearby. And similarly, local min is smaller than everything else nearby. And our focus last time was on global max and global min, and we're going to talk about local max and local min a little bit today. Now, do these things always exist? Well, no. It turns out that you can construct some really bad examples. There's really two things you need to make sure that you're always guaranteed to exist. And these aren't necessary, but they are sufficient. And they're pretty simple. Namely, we need to have our function be continuous. And when we look at an interval, it has to be a closed interval. So in other words, a less than or equal to x, less than or equal to b. So if we have those two things, we have a continuous function on a closed interval, then there will always, it's guaranteed, always, always, always be a global max and a global min for the function on that interval. Now, how do we find it? Well, what we do is we have a very simple process. Well, it has to happen somewhere. So the first thing we say, okay, where could it happen? Let's write down all the places, all the x values where our global max, our global min could happen. Well, certainly it could happen at the endpoints. So if our interval is between a to b, then our endpoints would be a and b. So we list those down. And then we list down these things, f prime equals 0, f prime equals undefined. Now, what are those? Those are called critical points. Critical points are where the derivative is 0 or the derivative is undefined. And we saw last time that when the derivative was positive, that our function was going up. And that when the derivative was going negative, our function was going down. And so at those points, we can't have a max or min. So that's why we threw those out. And what we were left with, well, one of these two options. Well, now we have a list where it could happen. We plug each point into our function. So we have a list of x values. We plug all the x values into our function. At the end, we have a list. And now what we do is we look at our list and we say, well, the largest value in that list is the max. And the smallest value in that list is the min. And that was the basic idea. Now let me say one word of warning. I didn't point this out last time. But there is a little bit of a caveat for these points here. So let me just the critical points. Let me just point this out with an example. Hopefully get the right example. So suppose my function is x over x squared plus 5, and I'm looking at the interval 4 less than or equal to x less than or equal to 8. Now, by the way, this is also notation 4, 8 with square brackets on the end. These two mean the exact same thing. Okay, so first off, if we were making a list of candidate points, definitely 4 and 8 make the cut because they're the endpoints. Endpoints always get listed as possible points where the maximum can occur. And then the next thing you look at is you look at the derivative. Now, I didn't write down the quotient rule here, but here would be a great time to use the quotient rule. So let's see, what do we say for the quotient rule? We take the bottom times the root of the top minus the top times the root of the bottom, all divided by the bottom squared. And we look at when is the function undefined, when is the function 0. Sorry, when is the derivative undefined, when is the derivative 0. Now, here, certainly the top is a polynomial, the bottom is a polynomial. The only place I could ever have to worry about it being undefined is if the bottom were 0. Do I have to worry about it in this case? No, because notice I have an x squared. If I always square, I get something positive, and then I add 5, making it even more positive. So the bottom is never 0. So really the only thing I need to worry about as far as critical points goes is when does this equal 0? Well, if I rewrite this, so I can ignore the denominator, I just care about the numerator. So this becomes x squared minus 2x squared, so negative x squared plus 5 equals 0. Or x squared equals 5, doing some mathematical wizardry there. And what are the possible values for x? Well, square root of 5, plus or minus. Now, do we add those to our list? No, and I didn't point this out last time, so let me point it out now. Because where are we trying to maximize our function? Well, we're maximizing it, finding the global maximum over some interval. So I only want to get the critical points in the interval. If it's outside of the interval, to me, it doesn't exist as far as the problem is concerned. It's irrelevant that there's a critical point at negative root 5. And if you think about what the value of root 5 is, it's somewhere around 2 point something. It's certainly less than 4. So in this case, the only points that make our list are 4 and 8. There's no critical points as far as finding the global max and global min are concerned. Now, I'm not saying that these aren't critical points. I'm just saying they aren't critical points inside our interval. So make sure when you're looking for critical points, you restrict only to those in your interval when you're asked to find a global max and global min. So now we're done. We've made our list. So now we do our second step. We plug each point into the function. So our function here is x over x squared plus 5. And plug in 4, you get 4 divided by 16 plus 5 is 21. Plug in 8, you get 8 over 64 plus 5 is 69. And this is larger, so this is the max. And this is smaller, this is the min. Okay. So that was my word of warning. So when we're looking for critical points and we have an interval, make sure you only look at the critical points inside the interval. Ignore anything outside the interval. All right. Now, when we finished last time, as I said, we were looking at global max and global min. Now, for us, it's really easy. We're not doing anything to really test whether it's a max or min. All we're saying is, well, let's just find the largest value. That's easy. But what if I'm asking find all the local max and local min? Because now it's not so much that I can just look at it right away and say, I see a number, it's a min or a max. I have to do something else. So that's today's first topic, finding the local min and the local max. Now, there's some good news for us. Well, first off, we can do the same problem on an interval. So we may have an interval a to b. We might say, find all the local mins and local max in the interval. But we don't have to. We can just say, here's a function. Find all the local min and local max. I don't care where it is. So if we think about what we did last time, we still have the same basic idea. Where can they occur? Well, they occur in the exact same places that global mins and global maxes occur. When we went through our reasoning for where the global min and global max were, where we made, okay, it has to occur at one of these places, there's nothing special about them being the global min and max. I said these are where they occur. So where can they occur? Well, they can occur at endpoints if we have them. Now, we may not have endpoints. But if we do, they can occur at endpoints. And they often do when you do have an endpoint. Where's the other place? At the critical points. So derivative is 0. Derivative is undefined, or does not exist. OK. So we know where to look for them. We look for them in the exact same place. So really, the first step is no different than before. What about the second step? Well, the second step, we just looked at the values of the function. And now that's not enough. Now we have to think more. So really, finding them is not hard. But what's hard is classifying. In other words, I have the x-coordinates. I know where they are. But I can't just say my function equals 10. Is it a min? Maybe. Max? Maybe. Neither? Could be. So I have to be able to distinguish max versus min versus something else. That's really what we want to talk about here. So we're going to come up with some tests. And today we'll do our first test. And we'll call it the first derivative test. And the reason we call it the first derivative test is that it will involve the first derivative. And because this is the first test. We've also come up with another test, maybe tomorrow or Monday, called the second derivative test. And that's because it will involve the second derivative. OK, so to classify them, I'm going to make an observation. Very simple. We've said this before so many times that by now, hopefully it's pretty convincing. If f prime of x is positive on some interval, so not just at a point, but let's say it's positive over some interval, what should our function be doing? Yeah, the function should be going up. So the function is increasing. And if we just think about the derivative being positive, means that whatever my function does, essentially the tangent lines mimic the behavior of the function nearby. I mean, that's the whole idea behind this local linearization stuff. So if the tangent line has positive slope, see the tangent line, we can see that clearly the tangent line is going uphill, so that's increasing. So if the tangent line is positive slope, the function is also increasing. OK. Now, this is sort of a wave your hands kind of argument. There's a more rigorous argument, but we have to establish another theorem first. OK. Well, lo and behold, there's a related fact. If the derivative is negative on some interval, what does that tell us? Well, probably it's something very similar. Function is, and then we think, what's the opposite of increasing? Decreasing, yeah. OK. All right. So intuitive. Your derivative is positive, you're going uphill. Your derivative is negative, you're going downhill. And these are the two observations that we're going to use to figure out how to find if a point is a local min or a local max, along with one other fact. And here is essentially the other fact. Between critical points, f prime is positive or f prime is negative. So it's either always positive or it's always either negative. So if you know where all the critical points are, You just mark them down, and you look at what's happening in between. What happens in between, it's always the same thing. It's either always positive or always negative. And I mean, it's a pretty intuitive thing. If you think about, okay, what could happen? Why couldn't it always be positive? Well, if it couldn't always be positive, then either one or two things happen. Either you went from positive to negative, but if you go from positive to negative, what do you have to visit on the way? 0. But where the derivative is 0 is a critical point. And I'm saying there's no other critical point between. Okay. The other thing is you could just skip 0. You could say, we'll just jump over it. But if you jump over it, you're into the case where you have an undefined derivative, where you have a derivative that does not exist. Okay. So these are the 3 basic facts. Okay, so how do we do it? What can I erase? Okay, so let's draw a few pictures. All right. Okay, so this is here's the first derivative test. Okay, so let's say A is a critical point. All right. So what I'm going to do is I'm going to draw a line here. And the line is supposed to represent the numbers system that we use, what we call the real numbers. And I'm going to mark A. And there might be some critical points below or critical points above. But essentially, they're just off to the sides. So I'm just looking at A. Now, if I think about it, to the left, the derivative either has to be positive or negative. And to the right, the derivative has to either be positive or negative. So I really have 4 pictures here. So I'm going to draw 4 pictures in. And I'm going to mark the 4 possibilities. So let's see, what's one possibility? One possibility is the derivative is negative to the left, and it's positive to the right. Or it could be positive to the left and negative to the right. Or it could be simply negative on both sides, left and right. Or it could be positive on both sides, left and right. That's it. Those are the only 4 things that can happen. And now we just pretty much draw a picture, and we're going to be able to figure out what happens. So what is happening here? I have my point A. Now, before A, what's happening to my function? My derivative is negative, which tells me what about my function? It's decreasing, right? That's one of the things we said. If the derivative is negative, the function is decreasing. Okay, so I know what's happening. My function is doing this. It's going down. It hits my point A. Then what does it do afterwards? It goes up, because my derivative is positive, means the function is increasing. Okay, let's look at this picture. I'm coming down. I stop. I go up. What is this? What do we call this? It's a minimum, right? Because it's a minimum. It's the smallest value, because I'm coming down to the, when I come into the left side of it, and I'm coming up as I go from the right side of it. So this is a min. So when I see a critical point where the derivative is negative on the left, derivative is positive on the right, just draw the picture. Negative means I'm going down. I hit my point. Positive means I'm going up. And you can see, I'm at the bottom here. That's a min. How about here? Derivative is positive, then negative. Derivative is positive means going up, increasing. I hit my value of my function. Derivative is negative, going down. I'm decreasing. Look at the picture. Where is A? Yeah, A is at the top. It's at a max. It's bigger than everything nearby. So this is a maximum. Okay, now how about here? Derivative is negative. I hit A, critical point, negative again. Well, let's draw the picture to see what's going on. So negative means I'm going down. I hit A, whatever it is, and then I'm going down again. So what kind of point is this? Is it a max? No. Is it a min? No. It's one of those neither points. Remember when we talked about the function x cubed last time? You may have remembered we drew this function in class, and we had this function x cubed. It did this. And we had a critical point at 0, but it wasn't a max or a min. So just because we have a critical point doesn't mean automatically we have a max or min. So this is what we call neither. Neither max nor min. How about here? Derivative is positive, hit my critical point, and then it's positive again. Picture, I come up, I hit my critical point, and I go up again. So this one is actually what's happening in the x cubed case. So again, same thing, this is neither. Okay. So essentially we have one of four things happens, and once we know what the value of the derivative is, we just look at it, and we can tell right away what's happening. Now, two things about the first derivative test. It's stronger than the second derivative test, and we haven't done the second derivative test, but we will soon. Not today, but another day. So the first derivative test will always work. Now, the hard part about the first derivative test is trying to figure out the signs. So if you're having a hard time figuring out the signs, and especially if you're dealing with the weird functions and weird angles, say like tangent, some of those trigonometric functions, you might have a hard time figuring out the signs. Second derivative is sometimes easier to use. First derivative will always work. Okay, is intuition good? Yeah? Okay. And it's easy to make functions which match all these behaviors, by the way. So this, here's an x cubed at x equals 0. Think of this as like x squared at x equals 0, negative x squared, this is negative x cubed. So all these four things can actually happen. All right, so now we come down to our procedure. Let's see. We can probably just do it here. So what did we do? We list all the candidates. Now, we don't have to do an interval. It doesn't have to be a closed interval. It can be any interval, or it could be the whole set of real numbers. So I'm going to cross this out. We do the same thing. We list all our candidates. There might be endpoints. If they are, we throw them in. If not, that's fine. We list the critical points that are in the interval. If there is an interval, if not, just list them all. And finally, we don't look at the value of the function. So when we do this test to figure out if it's a local max or a local min, we can plug it into the function, but to classify, let's do our local, and instead of finding, let's do classifying / finding. So this is the find. This is where they are, but we need to figure out what they are. And now you apply first derivative test. And classify. And what's the first derivative test? It's simply look at the derivative to the left and to the right of every single critical point. Now, the best way to see this is just to do lots and lots of examples. So we're going to do lots and lots of examples, at least as many examples as we can fit in 10 minutes. Hopefully that's lots and lots. Okay. Okay, so suppose my function f of x is x to the fifth minus 15 minus 15 x cubed plus 8. Here's my function. And I say find all local min and max. Now, I didn't specify an interval, so when we don't specify an interval, it's over all x values where the function is defined. In this case, from negative infinity to infinity. What's our first step? Yeah, we start with the derivative. The derivative is important because, first off, we use the first derivative test. So we better have the derivative at some point. But even before we apply the first derivative test is we have to find where to look, where to apply it. And the way we find where to apply it is to find the critical points. And the critical points come from the derivative. So yes, we start right away with the derivative. So what is the derivative of this function? X to the fifth, derivative. 5 comes down, x to the fourth. Minus 15x cubed becomes 45x squared plus 8 becomes 0 because it's a constant. Good. Now, this is obviously defined for all values of x. Let's set it equal to 0. So first thing to note, I can divide everything by 5. So that's the same as x to the fourth minus 9x squared equals 0. I can factor out an x squared. X squared times x squared minus 9 equals 0. Then, of course, I can factor this as x minus 3, x plus 3 equals 0. So where are the critical points? Well, we have this nice factored polynomial. Where is it equal to 0? Well, when x is 0, when x is 3, or when x is negative 3. So at 0, 3, negative 3. And now what we're going to do is we're just going to draw a line. And this line is all the numbers. Now I'm going to put on this line all my critical points. And in this case, I have 3 of them. I have a critical point at 0, and I have a critical point at 3, and I have a critical point at negative 3. Okay, so here we have our nice function. Now, to apply the first derivative test, I need to figure out the signs, whether positive or negative. So in particular, note I have 3 intervals here, all the way from negative infinity up to negative 3, from negative 3 to 0, from 0 to 3, and from 3 all the way to infinity. And I'm going to look at each single interval and figure out whether the derivative is being positive or negative in that interval. So how do I do that? Well, what I do is I just look at the interval and I pick a point. And it doesn't matter what point I pick. So suppose I'm from 0 to 3. What's the point between 0 and 3? 1. Now, you can pick any number. Your goal should be to pick a number that's not hard to figure out what's going on. 1 is a nice number. So I put 1 into this function, which is the derivative, not into the original function, to the derivative function. When I plug 1 in, what number comes out? You get 5 minus 45 is negative 40. The 40 is not important. The negative is. We only care about the sign. So when I plugged in 1 here, I saw that f prime of 1 is negative 40. The only important fact is that that's negative. So that tells me that my derivative is negative between 0 and 3. What if I come over here between 0 and negative 3? Well, I could probably plug in the same thing, negative 1. And I could plug it in. And if I plug in negative 1, lo and behold, you'll see you get the exact same number. And again, negative. OK, so let me erase this. So we know it's negative here, and it's negative here. OK, let's say something bigger than 3. 4. All right, 4 to the fourth, 256. All those, math, computer science, programming nerds, powers of 2. Yeah. 256 times 5. Oh, it's a big number. OK, let's jump down here. Because, really, this function right here, if I multiply by 5 again, this is the same as f prime of x. All I did was just factor it. So here, it may not be obvious what happens when I plug in 4, but here it's a little bit clear when I plug in 4. 5 is positive, x squared is positive, 4 minus 3 is positive, 4 plus 3 is positive. So when I plug in 4 into this, which is really the derivative written just in a different way, it's easy to see, here my derivative is positive. I don't know what the value is, but I don't need to know the value. I only need to know the sign. What about when I come over here? Negative 4. Well, I can do the same thing. 5 is positive. Negative 4 squared is positive because it's 16. Negative 4 minus 3 is negative. But negative 4 plus 3 is also negative. And 2 negatives make a positive. And so here, my derivative is positive. Now we look at our picture. And we can tell right away what's happening. So here, it's telling us that at -3, before we're coming up, and then we hit -3, whatever the value is at -3. Then after -3, we go down, because it's negative. So what do we know about -3? Yeah, so -3 is a max. The local max. Now, I could plug -3 in and get the actual value of the function, but right now I'm just caring about how to find whether it's a max or min. Now I'm coming down, I hit 0, and then I go down again, because my derivative is still negative. So what's 0? It's neither. It's not a max or a min. Now I hit 3. Now after 3, derivative is positive, so I'm going back up again. So what's 3? It's a min. I'm at the bottom. So I have my max and I have my min. All right. And now we found them. We can actually say more. Without doing any extra work, we get the following for free. And sometimes you might encounter a question like this. So on what intervals, it might be one single interval or several, is the function increasing? We don't have to do any more work. We just look at what we've written here, and we can tell you right away what's happening. So when I'm looking for where the function is increasing, we just translate that. Function increasing means the derivative is positive. So where is the derivative positive? Well, here it's positive. From negative infinity all the way up to -3, and then I switch signs. Okay, so I'm going to say from negative infinity up to 3, and you can include 3 if you want, or not. I'm not going to be that picky. Some people are that picky. I'm not. Is there anywhere else where the derivative is positive for an interval? Yeah, over here, right? Where f prime is greater than 0 again. So the other interval, so there's a 2 in this case, you start at 3 and you go all the way up to infinity. Now we can also ask a similar question. On what interval is f of x decreasing? So we again translate f of x decreasing if I, well, okay. Let me try to make it look legible. F of x decreasing, we translate that. Derivative is negative. Where's the derivative negative? Well, certainly it's derivative is negative between -3 and 0. It's also negative between 0 and 3. We might as well just put them together. Yes, thank you. Okay, it should be -3 on the top. Thank you. So here, -3 to 0 and 0 to 3, might as well just slap them together since they already share 0. So -3 up to 3. All right. So when you do the first derivative test, automatic bonus, you can answer questions about when is the function increasing and when is the function decreasing. Okay, let's try another one, since it's always good to practice. Suppose g of x is x to the 2/3. Oh, if I don't get my number right, we're going to get in trouble. Okay, minus 2/9 x cubed. So this is a function, and it is defined for all values of x. Because I can always take the cubed root of any number, positive or negative. And it's really positive to begin with because I'm thinking of it as x squared, and then I take the cubed root. Okay, so here's my function. So what's our first step? Derivative. Whenever we're doing anything with local max, local min, we really need to start with the derivative, because that's going to give us where our critical points are, and then we're going to either use the first derivative or second derivative, today first derivative, to figure out what they are. So what's the derivative of this function? Well, 2/3 comes down, x to -1/3 minus 2/9 times 3x squared. Or if you like, that's 2/3, and the 3 goes into there, so I can factor out 2/3. That's a common x to -1/3 minus x squared. Okay, so critical points. Is the derivative ever undefined? Yes. The derivative is undefined. Now, the function is always defined. The derivative, in this case, isn't always defined. Where do we run into trouble? See that exponent being negative? That's really the same as saying the following. This is really the same as saying 1 over, and if I want, I can write it as the cubed root of x. So x to the negative 1/3 is the same notation as saying 1 over cubed root of x. Now, what's our problem with this one? When x equals 0. When x equals 0, we're trying to divide by 0. So it's undefined at 0. So 0 is a critical point. Okay, so where do we write this? G prime of 0 is undefined. Okay. So 0 is a critical point. Oh, critical point is spelled the other way. All right. So here's one of those cases when we have the derivative as being undefined. Now, where else is another critical point? Well, we set it equal to 0. That's the same as saying x to the negative 1/3 is equal to x squared if you set it equal to 0. And if you play around with it, that's the same, multiply both sides by x to the 1/3, that's the same as saying that 1 is equal to x to the 7/3, which is 2 plus 1/3. Well, what number, when I raise it to a power, gives me 1? There's not very many of them. Yeah, in fact, there's only one that does it. It's 1 to any power always gives me 1. And in fact, the only way I can take a number and raise it to any power and get 1 is to start with 1. So this is x equals 1. Okay, so g prime of 1 is 0. So 1 is also a critical point. Okay? So here we have 2 critical points. So let's draw our line. Here's all our numbers. I mark the number 0 somewhere. I mark the number 1 somewhere. And now I go through and I just start thinking about what happens. Okay, so I need to figure out whether the derivative is positive or negative. Now, here's one of those times when we have to be really careful. So let's pick a number from these intervals. So let's pick a number smaller than 0. How about negative 100 billion? Now, why do I like negative 100 billion? Well, when I have negative 100 billion, what happens to this term? It's tiny. Teeny, 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 tiny. If I choose a huge number, because it's 1 over something. So really, for large values of x, I only see this negative x squared. This is insignificant. Okay, so what does that tell me? It tells me that if I choose a really huge negative number, my function looks like negative 2/3 x squared. So the derivative looks like negative 2/3 x squared. So what's the derivative in this interval? Negative. You can plug in numbers and try to figure it out. I'm just saying pick a huge value so big that this is essentially insignificant. And then your derivative looks like negative 2/3 x squared. If you like, this is, I'll even write down, approximately negative 2/3 x squared for x large. Similarly, if I'm really big over here to the far side of 1, what's my derivative over there? Again, same basic reasoning, it's negative. So imagine I choose like x is of 100 billion. Again, my derivative is roughly negative 2/3 x squared, which is a negative number. Now, 0 and 1 is the hard part. Okay, so let's pick a number between 0 and 1. Anyone have a favorite? 0.1? We have to take a cubed root. How about we try an 1/8? Now, why an 1/8? Well, I choose an 1/8 because do we know what the cubed root of an 1/8 is? It's a half, right? Yeah, 1 over 2. So when I plug in an 1/8, I can actually numerically compute this. So the moral is you can pick any number. When you have a calculator, go with whatever works. When you can't pick any number, go with something you can actually work with. I just thought of 1/8 because, I can figure out cube root of an eighth. All right, so when I plug in an eighth, g prime of an eighth, well, we get the 2/3 times this x to negative 1/3 will become 2. And then minus 1/8 squared, which is 1/64. Okay, so that's g prime of an eighth. 2/3 times 2 minus 1/64. Well, I started with 1 cube root of x. So cube root of an eighth is a half, so 1/2 becomes 2 again. Okay, so 2 minus 1/64. Is this positive or negative? Positive. Okay. And now we just read it. It's negative, positive, negative. So 0 is a min. 1 is a max. We can just see. When the derivative is negative, then positive, our picture looks like this. So it's a min. Positive, then negative, our picture looks like that. It's a max. All right. I'd love to do one more example, but I guess I'll just have to throw that on the midterm. And instead, I have to jump and talk about another theorem. Well, maybe I'll do it for an example next time. Then we can save a more fun problem for the midterm. I got very excited this morning. I was in my office like, oh, I know what's coming up. I have a great one. Students are going to love it. Very similar to what we just did a few minutes ago. Okay. We'll do one more example next time. But I need to mention one theorem because it shows up on the homework, which is due on Friday. I didn't mention it at the end of last class, which I should have. This is called Rolle's theorem. And Rolle's theorem tells us something. If we have some very simple conditions on our function, we can say something about the derivative. Now, what are the simple conditions? Well, the simple conditions are f is continuous on an interval a to b. So a less than or equal to x, less than or equal to b. Look like an a. So I have some interval. My function is continuous on that interval. That's the first condition. Second condition, f is differentiable. Now, to say it's differentiable just means I can take the derivative on the interval a less than x less than b. So I don't care about the endpoints. Usually, most of the time, it's differentiable at the endpoints anyways. But so it's continuous, and it has a derivative. That's essentially what's going on. We have those two facts. Continuous, it has a derivative. And the third thing is that the function at a is equal to the function at b. Okay, so these are our assumptions. If we have the following three facts, it's continuous, it's differentiable, and I end and start at the exact same value for the function. So the function at a equals the function at b. These three things being true implies there is some point C, where C is strictly between A and B, where f prime of C is 0. In other words, this is a way to guarantee I have a zero derivative someplace. So if you start and end at the same height, somewhere you had to be 0. And the pictures, the proof, it's fairly intuitive. So what's going on? Well, you have A, you have B, and their value of the function is the same. So you start and stop at the same height. That's what f of A equals f of B means. Now, what happens? Well, one thing that could happen, how can you get from A to B? It has to be continuous, so you can't jump around. It has to be smooth. Smooth is the same as differentiable. Don't have any weird things. Well, one thing you could do is just draw a straight line. Okay, that's true. You could do that. But then it's trivial, because what's the derivative of a flat straight line like that? 0. So at any point I pick between A and B works. Okay. So let's suppose I don't have a flat line like that. Well, what could I do? Well, I might go up. I might come back down. But now, here's the trick. If it's not a flat line, either I went up someplace or I went down someplace. And what do we know? We know that when we have a function which is continuous on an interval, it has to have a max, a global max. It has to have a global min. So in particular, you either have something that looks like this, where you have a global max strictly up above here, above the value f of a and f of b, or you have a global min strictly below this value. You could actually have both. You might have something like this, where you have a global max and you have a global min going out at the same time. But why is that important? Where do we know that global maxes and global mins can occur? They occur at the endpoints, and then we're basically arguing, well, there's some place besides an endpoint where it occurs, and they occur at critical points. Okay, but what is a critical point? A critical point is either where the derivative is 0 or the derivative is undefined. But look at this nice fact. This tells us the derivative is never undefined, because we can always take a derivative. That's what this means. To be differentiable means I can always take a derivative. So it can't be undefined. So the only thing I can be left with is that where this global max is a place where the derivative is, in fact, 0. Okay. So if you were to look at the tangent line here, at the global max, you'd see it has a flat tangent line. Or it might happen at the global min. But that's essentially the argument. Now, there's one other theorem which is like this. Let me mention that theorem as well. And we'll do it a little bit more with it next time. Just practice it. And it's called the mean value theorem. In this theorem, very similar assumptions. F is continuous on the interval a less than or equal to x less than or equal to b. And F is differentiable on a less than x less than b. So notice it's essentially the same thing as you had for Rolle's theorem. Same basic facts. Now, we're not going to assume that f of a equals f of b. And here's the conclusion. If we have these two facts, then there is some c with a less than c less than b. So again, as before, there's some point in between a and b such that f prime of c, now in this case, it's not 0. It's equal to f of b minus f of a over b minus a. That's the mean value theorem. Now, if we think about this, we've seen this kind of expression before. In fact, we saw this way back at the very beginning. In the beginning, we said, let there be ratios. And there were ratios. And what was this ratio? This is the slope of a secant line, but we also said it was something else. It represented something else. It represented a rate of change. What kind of rate of change? This was the average rate of change. Between A and B. And what did this represent? This f prime of c. That's also a rate of change, but it's not the average rate. It's the instantaneous rate. So the way you can think about this is it says that if I go between af of a and bf of b, at some point I was going exactly the average. So for instance, if you drive 120 miles in 2 hours, what was your average speed? 120 divided by 2, 60. This says there has to be some point when you're going at exactly 60 miles per hour. That's essentially the theorem. So we'll talk about this more next time. Don't forget, homework is due on Friday. I do have office hours this afternoon and Friday morning. Have a good day.